This video is about graphing exponential functions. We're going to start with looking at the basic parent graph equation, y equals b to the x power. When you graph that equation, of course, it is a growth function. It is approaching the x-axis on the left side and rising on the right side. It goes through the y-axis at the point 0, 1, so the y-intercept is 0, 1. There are no x-intercepts. It does not cross the x-axis with the basic parent graph. Exponential functions have an asymptote. For some of you, asymptote may be a new term. An asymptote is a line that is a boundary. It kind of shows a boundary to the graph. We draw asymptotes with a dotted line to show that boundary. Asymptotes do go on forever. You have all kinds of asymptotes, vertical, horizontal, or oblique, which are slanted. But with exponential functions, we just have a horizontal asymptote. This particular asymptote is at the boundary of the x-axis, which is x equals 0, that horizontal line. For exponential functions, the domain, negative infinity to positive infinity, all real numbers. The range is all the y values from that x-axis up, but it doesn't touch the x-axis, so that's why it's not equal to 0. So from 0 up, but not equal to 0. So these are the basic characteristics of exponential functions when you graph them. Now, of course, when we get into the transformations, we'll look at some differences that can occur with that exponential graph. So let's look at the transformation equation. So we have y equals a times b to the x minus h plus k. So just like with other equations, we have values that can go in this location, the value in the k, the value for a, and all of these values will have specific meanings and will do specific things to the equations. Just to review a little bit, let's remember that the value b, which is the base, has to be greater than 1. And when that value is greater than 1, we have a growth equation. But when that value b is between 0 and 1, we have a decay situation, which means that it reflects over the y-axis and turns around. So I just want to point that out to you again. So just remember that we have this situation when b is greater than 1, and we have that decay situation when it is between 0 and 1. So growth versus decay. We've talked about that before in our previous videos. Now, we also can reflect when this value of a changes. So if the sign of a is negative, then that will cause the equation to reflect also, and that will make it also change and have a reflection over the x-axis. So that is also going to change what happens to our graph just by a sign change. Now, also a change in the base of the equation will make values change. We talked about the growth and the decay, but also a change in the value of the sign at the top. So if we have a sign change of the exponent, that will make it reflect over the y-axis also, and that will make it be the same as that growth and decay. So that is also something that can happen that will be similar. So I just want to point that out, that can happen also. So sometimes in that equation that can also happen. So let's talk about the h value. What can that h value do to the transformation? This is going to be a horizontal shift, which means it's going to move left or right. Just like our other equations, it's going to be opposite the sign. So a positive value is going to shift it left, while a negative value is going to shift it right. The k value is going to be a vertical shift, so that's going to move it up or down. And that is going to be based on whatever sign. Positive is going to shift it up, negative is going to shift it down. The a value itself is going to be a vertical stretch or shrink. So if a is greater than 1, it's going to be a stretch, where if a is between 0 and 1, it's going to be a shrink. So kind of like things that we have looked at before with other functions, same thing can happen with our exponential functions. So let's look at some specific examples. We've kind of done the rundown on what the values in particular locations will be. Let's look at some particular things. If we have horizontal shift, that will not change the asymptote, but a vertical shift will change the location of the asymptote. If we have a change of over the x-axis and vertical shifts, that will also change that asymptote. So we have to kind of watch what happens to the asymptote. So let's look at an easy one to begin with. If we have y equals 2 to the negative x power, if we were to graph that particular problem, we said that the sign of the exponent is going to change it similar to growth and decay. So that is going to reflect it over the y-axis. So normally we would be having a growth pattern. So that is going to change it, and it's going to become a decay. So our graph is going to look like that. It will still have the same y-intercept of 0, 1. The asymptote will still be in the same location at x equals 0. It will only change the reflection over the y-axis. Now let's look at an equation, y equals 2x plus 3. That equation is using the k value, so that is going to be a vertical shift. That's going to shift it up 3 units. So that means that the asymptote is going to shift up 3. 1, 2, 3. So if we draw that asymptote in first, that kind of helps give us the boundary. And so now our point, instead of being at 0, 1, it's going to be at 0, 4. And our graph is going to basically look the same, but only it has been shifted up 4 units. If we have the equation y equals 2 to the x minus 4, that graph is going to shift to the right 4 units. So in this particular graph, our asymptote is going to stay at the same location, x equals 0. It's going to make our intersection point change from being 0, 1 to being 4, 1. And there is our horizontal shift for that particular graph. Asymptote's still the same. Domain and range is still the same. The domain does change on this vertical shift here that went up 3 units. How did the domain change? The domain is still the same, all real numbers, but the range changed. How did the range change? This domain is still negative infinity to positive infinity, but how did the range change? In this case, instead of being greater than 0, this range became greater than 3 with that vertical shift. So we do have to watch vertical shifts as it's going to affect the range of our functions. Now for our last little bit, let's look at a stretch before we finish up. We have y equals 3 times 2 to the x. That number being bigger than 0 is going to make our graph stretch. Our asymptote still is at x equals 0. It's still going to go through our point 0, 1 for the y-intercept, but that stretch is going to make it rise much quicker. Whereas y equals 1/2 times 2 to the x power, that graph is going to make our graph not rise as quickly. So it flattens it out a little bit more. Again, that y-intercept still at 0, 1. Asymptote still at the same location. Domain and range still at the same. But this is a shrink. It's shrinking away from the y-axis, where this stretch is shrinking it up, or stretching it up to the y-axis. The last part of our graphing exercise is to look at a special exponential value that is called e. E is an irrational number, and we won't go into how the e value was found. If you were in an advanced math class, you'd go into the hows and how this value was determined. It's basically found by calculating formula 1 plus 1 over n to the k power, where n goes to infinity. And you keep calculating that value, and e is the value 2.718, and it goes on forever. That's what irrational numbers do. So e, we say that e is approximately 2.718. It has a special value. So we also have graphs for e, y equals e to the x power. And there is a special e key, usually on most calculators, where you can use that to graph. The look of the graph is still the same, regardless of the base. It's still going to go through that point 0, 1. It's still going to look basically the same as other graphs. It still has the same asymptote at x equals 0. It's just you have that special base value that's called e.